only this percentage of people who watch are subscribed. So subscribe now and never miss out. Enjoy the video. Today's episode was brought to you by the letter G for Giganotosaurus, and by the number... What?
That's not how it's pronounced, I don't think.
What? Oh, there's an O in there. So it's Giganotosaurus then.
I don't know. The first G... let's do it a few different ways and we'll pick the right one later.
If you say so. Today's episode was brought to you by the letter G for Giganotosaurus. 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 Today's episode was brought to you by the letter G for Giganotosaurus, and by the number 107, which is how many papers we combed through to make it possible. Enjoy. Do you think we got it?
I think we're good.
Splendid! Our picture of Giganotosaurus is very incomplete. It's not that we don't know, like our picture in broad strokes of giant Carcharodontosaurids is pretty good. The problem is saying certain particular things about Giganotosaurus is burdened. Filling in gaps of its anatomy is somewhat uncertain because its close relatives vary in important respects, and there's more gaps than we should have because, yes, we are missing bones from the holotype, but some of the bones we have never been properly described or never been figured. We're accustomed to soft tissues of an animal being open to interpretation because they don't fossilize, at least not often, so, the extent of the horns and claws. How much flesh should we put on the throat and the belly area? What kind of integument does it have? Is it feathered? Is it scaly? Is it both? What colors was it? Those were used to being educated guesses, but with Giganotosaurus, some aspects of the skeleton are like that. Different workers will credibly come to different conclusions about the size of the arms, the length of the feet and the toes, the height of the spine, the depth of the torso, the size of the back of the head, the shape of the tip of the snout. These are not problems one expects to encounter in an animal as popular as this one. It occurs to me that we've never actually explained what a description is. I always say, this animal was described in such and such year by such and such person, but what does that mean? We say that material has been described when an author has gone through the fossil bones and whatever else they have, element by element, and described it in technical language. These tend to be impenetrable to the layman because they're filled with jargon, but they're not really intended to be journalism or science communication. A description is more like sheet music or a computer program where people who know how to read it can reproduce what the person who wrote it was observing. Crucially, it means that you can work with the material without having physical access to it. Unless you need like histology or isotopes or something. But ideally, you will include figures, either line drawings or photographs, or even 3D scans of the bones, though that's still pretty rare. Strictly, to establish a new species, you only need to describe the elements pertinent to the diagnosis. Which, by the way, I love that we call it that. It's like a disease. Like, I'm sorry, your skeleton has a bad case of Giganotosaurus. It's terminal. But in a preliminary description, you're just trying to provide enough information so that if somebody comes along with new material, they can check it against your description and be like, well, this bone is shaped like this, and this bone is shaped like this, so it's a different species. That's the minimum. That's if you're Othniel Marsh and you have 7 more species to name today. Conscientious workers will include as much as they can, but you can't include everything, either because the specimen is still being prepared, or some of it is still in the ground, which sometimes happens, or if you're publishing in a physical journal and pages cost money, and osteology tends to fill books. There's plenty of fossil animals that are in this situation or were in the past where they have been around for decades. People have been working on them. There's been a preliminary description, but they're still waiting for a full osteology to be published. Giganotosaurus is not unique in this respect. What's weird is that it's been sitting there being extremely popular for 27 years as our understanding of Carcharodontosaurids and its entire formation has like crystallized around it. It's like a background character in its own setting. So if, for example, you're trying to put together a video about it, you have to either go to Argentina to see the bones for yourself, find a museum that has a mount of the specimen, and trust that that mount accurately reflects the material, which we'll get to, or comb through papers looking for scraps, finding little places where they're like, as in Giganotosaurus, this bone is shaped like this, and so forth. I did the third one. This animal is from the Cordilleras Formation in the Neuquén and Rio Negro provinces of Argentina. This is Albian and Cenomanian rock. We're interested in the upper Cordilleras, so Cenomanian, right around 100 million years ago. The terminology for this rock has changed over time. Originally, it was just the Rio Limay Formation with one undifferentiated Limay fauna. Nowadays, it is 3 separate formations. Cordilleras at the bottom, and above that, the Winkle Formation, which is Cenomanian and earliest Turonian, and then above that, the Cerro Lisandro Formation, which is entirely Turonian. We're interested primarily in the Cenomanian portion of Cordilleras, but we're also going to be referring to Winkle because there's some animals in there that are relevant to our understanding of Cordilleras, which is funny because as late as the early 2000s, Winkle had a reputation as being like fossil poor. You're not gonna find anything out there. And now it's got like more animals than Cordilleras. Strictly, the first material from Giganotosaurus was found in 1987, but this was just an isolated jawbone, just part of the front of the dentary, where the chin meets. It was not clear that it was Giganotosaurus until we had the holotype, which was found in 1993 by a fellow named Ruben Carolini, hence the specific name, Giganotosaurus carolinii. Giganotosaurus means giant southern reptile, because it's very large and from South America. It was found in Neuquén province on the northern side of the reservoir there. The reservoir is held in place by a dam at a town called El Chocón, and El Chocón has become kind of a hub for paleontology in the area, and Carolini has gone from amateur fossil hunter to the director of the municipal museum there. El Chocón is apparently quite proud that Giganotosaurus is from their town. They have this big life-sized statue greeting visitors to the place, and it's hideous. I love it. It was immediately apparent that this was an enormous animal. In 1995, Correa and Salgado described it somewhat and estimated its size at 12.5 meters long. That estimate has actually held up pretty well. Like, we don't have a complete tail from the animal, so we'll probably never know its exact length, but estimates are right around 13 meters, and they vary by less than a meter. The isolated jawbone, which was described as a second specimen of Giganotosaurus in 1998, is a bit bigger, so tends to be estimated at above 13 meters long for that animal. Now, in 1995, our understanding of theropod evolution in the Cretaceous was still developing, as it is to this day, but for a very, very long time, the conventional wisdom was that allosaurs were the ancestors of tyrannosaurs. And as Pangaea split up in the north, allosaurs gave way to tyrannosaurs, whereas in the south, they disappeared and ceratosaurs in the form of abelisaurids took over. 2 developments challenged that. In the early 90s, we had confirmation that tyrannosaurs are actually derived coelurosaurs. That idea had been around since the 1920s, but modern phylogenetics were required to really prove it. And in the late 90s, it was confirmed that allosauroids are not an evolutionary grade leading to tyrannosaurs. They are their own branch of neotheropods. Giganotosaurus was discovered right in between those 2 developments. So in 1995, Carcharodontosaurids consisted of just Carcharodontosaurus itself, Stromer's animal, and that material had been destroyed in World War II. Acrocanthosaurus was known, but it wasn't put in with Carcharodontosaurus, it was in with the other allosaurs. Correa and Salgado didn't mention Carcharodontosaurus at all in their description. They placed Giganotosaurus as tetanurae theropods more derived than megalosaurids, but outside allosauroids. While that was going on, workers were refining Carcharodontosaurus. The new material coming out of the Chemkeb beds in North Africa had been described by Sereno and numerous co-authors, and I think that is the first place that we see Carcharodontosauria as we currently understand it, where it has Giganotosaurus, Carcharodontosaurus, and Acrocanthosaurus all in it. Though, interestingly, they recover Acrocanthosaurus and Carcharodontosaurus as the more derived members, and Giganotosaurus is more basal. But word of Giganotosaurus was spreading. I think the very first artistic representation of this animal was actually in 1995's Dinotopia: The World Beneath, where he portrays it. I think he just started drawing a larger Tyrannosaurus and then found out about Giganotosaurus and decided to turn it into one, because this is a very Tyrannosaurus-looking Giganotosaurus. It's especially apparent on the next page, where it's clearly just a Tyrannosaurus face with some extra bits slapped on. The first wave of scientifically rigorous paleo art of this animal was by Bob Walters and Tess Kissinger, who I think were largely drawing from a reconstructed skeleton done by Mary O'Donnell and her team. O'Donnell had been doing this kind of thing, preparing and reconstructing skeletons in California for like 40 years, but Don Lessem commissioned her to go down to Argentina and help make a Giganotosaurus that they could then make a cast of to exhibit in the United States. That exhibition was called T-Rex Meets His Match. So between that and the Dinotopia spread, where it's facing off against a T-Rex, like we've been framing this as a prize fight from the very beginning. Anyway, that was in 1996 and 1997, which was just in time for collection of a related animal, Maplusaurus, from the Winkle Formation to start. This animal is so similar to Giganotosaurus that it was initially thought that it might be a second species, but importantly, it is also fragmentary, but it lets us fill in some gaps. And its description includes a bunch of figures and a bunch of complete descriptions of the bones. Meanwhile, we were getting more complete descriptions of Acrocanthosaurus, crucially a complete skull that was preserved intact. We got the endocranium of Carcharodontosaurus was described, the brain case of Giganotosaurus was described. These were the developments that clarified that Carcharodontosaurids are allosauroids. And you might ask, why was that so hard? Well, when theropods reach gigantic sizes, their anatomy veers in certain directions, and there are convergences between otherwise distantly related animals. Both Carcharodontosaurids and Tyrannosaurs have thickness and fusion of the brain case and enlargement of the pubic boot. Carcharodontosaurids and Abelisaurids have similarly shaped sacrum, the part of the spine in the hip, and have, in some cases, very similar looking teeth. And all three groups have an extensive air sac system along the spine and very tiny arms for their body size. Nowadays, we know that these convergences do not mean that these animals are closely related, but that was not always clear. As a consequence, what we call Carcharodontosaurids had been placed in a more derived position as a grade between Allosaurs and Tyrannosaurs in the early 90s, or as Tyrannosaurids in the early 60s, or in a more basal position as Megalosaurids in the late 60s, or as Ceratosaurs, as sisters to the Abelisaurids in the late 90s. So before 2005 and 2006, which is when Tyrannotitan, a related animal also from South America, and Mapusaurus were described, what animals you were going to use to fill in the gaps in Giganotosaurus was a matter of opinion. And nowhere is the want of material, or properly described and figured material at least, more felt than in trying to restore the head of this creature. So what do we have? Well, 80% of the skull, apparently. They found it disarticulated. The bones were spread out over a 10 square meter area. I'm sure it was a huge pain to recover. But we have a partial maxilla, that's the upper jawbone, the upper half-ish of the eye socket and eyebrow, a complete brain case, which has had a detailed description, as has the inside of it, the endocranium. We have both quadrates, which are at the back of the head, and the front of the dentary, the chin. Now, from research mentioning the material and from museum displays of known versus unknown bits, we also have a partial premaxilla, which is this tip of the snout, partial nasal or nasals, which is the top of the snout, and the rear end of the lower jaw, where it hinges against the upper part of the skull. So how we fit those pieces together and restore the missing pieces is open to some interpretation. Reconstructions tend to cluster around two poles. I call them Boxycarnosaur and Notched Triangle. Boxycarnosaur has a high snout with a relatively blunt tip, a nice straight tooth row, and the back of the head is closer to straight up and down. It winds up looking a lot like Acrocanthosaurus. The notched triangle look is what we see in the Mereodono reconstruction and most mounted Giganotosaurus skeletons in museums, which I think are based on O'Donnell's reconstruction. This has a very squashed snout with a very long premaxilla on the front, a really snarled looking maxilla where at the back of the tooth row there's like this upturn, and the back of the head is much more slanted. Now, you might be tempted to say, well, the truth is somewhere in the middle, right? Maybe, but it's much, much closer to the Boxycarnosaur Acrocanthosaurus reconstruction. In 1995, they didn't estimate the total length of the skull. They had a rough figure, mostly just showing these are the bones we have and where they approximately would be, and that looks like they were thinking it was a 1.6 meter skull. In 2022, some authors with some new material to work with, which we will get to, estimated Giganotosaurus' skull at 163.4 centimeters. I love that they said estimate of about and then provided millimeters, but the actual number does have some wiggle room. It's actually between 158 and 169 centimeters. This safari toy, which is from 2017, takes the weird expedient of keeping the old notched triangle reconstruction of the skull and just shrinking it down until it's around 1.6 meters. Which, no, the core of the upper skull, the maxilla, antorbital fenestra, and orbit area is pretty well understood. It's the shape of the skull in front of and behind that and the shape of the jaw that is up for interpretation. The first thing you'll notice when you see a Giganotosaurus, or any Carcharodontosaurid really, is that antorbital fenestra is bonkers. It's so huge and open, and it makes sense. It's a weight-saving strategy. It allows them to have a very large skull without it being enormously heavy, but compare that to what tyrannosaurs are doing, where it's a much more segmented area in front of the eye. This, you could like put an entire smaller theropod's head inside its antorbital fenestra. Giganotosaurus is unique among Carcharodontosaurids that the maxilla, the upper jawbone underneath the antorbital fenestra, is not forming this large triangle. The upper and lower edges of it are almost parallel. It's like this big beam, big rectangular beam on the side of its face. There were pieces of the maxilla that were figured in the 1995 description, but then didn't get a nice shiny new photo in a 2013 paper, so I don't know what's going on with those. Suffice to say, the forward and backward extent of the maxilla material we have is unknown to me. There might be more there, though. The second thing people notice about Giganotosaurus would be that big square chin. It is, even compared to its close relatives, really flat and high. The dentaries, like the maxilla, form these big beams. And you might reasonably ask, well, why does it need such a robust chin? There is precious little functional analysis of Giganotosaurus. There's a little bit to go on for Carcharodontosaurids more generally. We know that Acrocanthosaurus has an intramandibular joint, like we talked about in Herrerasaurus, where the front of the jaw can slide and pivot a little bit on the back of the jaw. It's reasonable to infer that Giganotosaurus had something like that going on. There's several features of the articulation between the back of the skull and the first neck vertebra that suggest that Carcharodontosaurids had a lot of mobility, especially side to side, between the head and the neck, which makes sense. We're going to talk about how muscular the neck was. Now, in the early 2000s, the thinking was that where tyrannosaurs had been adapting famously for very strong bites, for high bite forces, Carcharodontosaurids, instead of bulking their jaw muscles outwards, they lengthened their jaw muscles front to back, which is an adaptation for being able to snap their jaws shut very fast. And I don't know if that idea actually holds up anymore. There was a 2010 paper looking at the bite mechanics of a whole bunch of theropods, and they included Carcharodontosaurus, which weirdly converged with Ceratosaurus of all things in having a high efficiency bite that, as far as I can tell, was limited to like the back of the tooth row. It's similar to the reconstructed state for the ancestral theropod condition, whereas other large theropods like Tyrannosaurs or Allosaurs or Abelisaurs have high efficiency bites across their entire tooth row. So at first I thought that, okay, well that makes sense, that having this giant mobile skull and a fast bite justifies having these huge joist-like upper and lower jaw bones. But now I'm not even sure if that's what it had going on. Since we're talking about bites, we may as well talk about the teeth. The number of maxillary teeth is unknown, but it was at least 12. So add to that 4 premaxillary teeth, you get at least 16 teeth in the upper jaw. The lower jaw had at least 15 tooth sockets, but the larger specimen, which has more of the jaw preserved, cuts off right at the 15th tooth socket, so there credibly could be 1 or 2 more there. Despite the name, carcharodontosaurid teeth are not especially similar to carcharodons, that's the great white shark. I think Stromer called them that because both animals have denticles forming serrations on the leading and trailing edges of the teeth, but most toothed theropods have those. It's an adaptation for cutting through tissues, cutting through flesh. The denticles we see in theropod teeth are a bit different structurally from what we see in sharks or in modern carnivorous lizards, because they need to hold up a lot longer. See, sharks and lizards replace their teeth pretty often, but a theropod could take 2 or more years to grow a new tooth. And as the tooth grew, the denticles folded the enamel and dentine together in between them, which gives it structural strength and makes it better able to hold up to 2.5 years of damage, while still being relatively small and closely packed. Zooming out, the teeth are blade-like. They are narrow side to side and triangular. They curve backwards along their length. Carcharodontosaurids specifically show these undulations or waves in the enamel on the edges near the serrations and sometimes spreading across the entire tooth. The function of those is a little unclear. It might be like corrugation, where it strengthens a sheet of material, strengthens the enamel. It might be like those furrows in a deli slicer. It keeps tissues from sticking to the tooth. But whatever their exact purpose, these were clearly teeth designed for macropredation. These were for cutting tissues off of a carcass. These were not the teeth that you would see in an animal that's snapping at fish. They're also not an animal that's crushing bones, at least not large bones. You might have been surprised a second ago when I said there were 4 teeth in the premaxilla, because it was very fashionable from the late 90s until, well, now, really, to reconstruct Giganotosaurus with a very long Allosaurus-like premaxilla. I think that originated with the late 90s reconstructions of Carcharodontosaurus, but the description of Acrocanthosaurus should have put that idea to bed in 2000. The 2010 redescription of the material even includes details of Giganotosaurus's premaxilla, where it is higher than it is long, unlike Allosaurus, and it has 4 tooth sockets in it. Maybe if somebody had figured Giganotosaurus's premaxilla, that could have cleared this up. I brought up length estimates earlier. The back of the head has the largest impact on how long you reconstruct the entire skull to be. In the late 90s, once we had more complete Carcharodontosaurus skulls, that animal was getting reconstructed as right around 1.6 meters for skull length. So in 1998, Calvo described the second specimen of Giganotosaurus, which, as I said, was a little bit bigger, and thought that Giganotosaurus holotype had a skull of 180 centimeters long, but then the new specimen could have been 195 centimeters, which is enormous. How do you get a skull that big, you may ask? Well, we have a complete brain case from Giganotosaurus, but the contacts between that brain case and the rest of the skull are not preserved. So they just tilted the whole brain case forward, taking the quadrates along for the ride and moving the quadrates back from the occiput a little bit, both of which extend the temple, make the lateral temporal fenestra really, really huge, and make the bar underneath it, the quadratojugal and part of the jugal, really long. Now, I can't prove it, but I think that this long-templed Ceratosaurus-like reconstruction is actually based on Abelisaurus. See, I mentioned earlier that there was this idea in the late 90s that Carcharodontosaurids and Abelisaurids were actually sister taxa, like a homegrown Gondwanan separate lineage of large theropods, and that idea died pretty slowly and piecewise. Like as late as 2002, there was an idea that Abelisaurus itself might be a late surviving Carcharodontosaurid. That's because Abelisaurus itself is a very Carcharodontosaurid-like skull, because as we said earlier, giant theropods converge. But look at the back of Abelisaurus's head. It has a giant lateral temporal fenestra with a very long bar underneath it, just like this. If the idea was percolating in the late 90s that these animals might be closely related to Abelisaurids, then it might have been reasonable to reconstruct it using that animal. Again, I can't prove any of this, but it would make sense. Anyway, doing this has multiple implications. It makes the skull much, much longer, obviously, but a lot of that length is actually behind the occiput, behind the joint where the head connects to the neck. So the whole head in the O'Donnell reconstruction has to like hang off of the neck, which is exactly how it's usually mounted. It's very odd to have the whole head underneath the neck like that. And as you lengthen the head, obviously you have to lengthen the jaw, which means that this jaw has to be incredibly long. This toy, which is not good, if that wasn't obvious, this toy cheats. They actually have the jaw articulating like at the jugal, right behind the eye there. They have the back of the quadrato jugal is just embedded in the neck somehow, which is a solution. By the 2010s, some authors had noticed that this way of reconstructing the back of the heads didn't really hold up. Like notably, Gregory Paul pointed out that we were reconstructing these way too long, though he also thought that Giganotosaurus was a species of Carcharodontosaurus, because of course he did. But you couldn't prove that Giganotosaurus' skull didn't look like this. I couldn't prove it. Like, I was writing this episode and I was banging my head against this, like, am I gonna have to just explain that the people who know the material best reconstruct it this way, but every other Carcharodontosaurid seems to have a different arrangement, and we don't have a squamosal from this animal, so I can't prove that they're wrong, and it's I feel uncomfortable calling them out on this, but then it was like a sign from God. Meraxes, a 2022 genus, was named right while I was working on this. It's called Meraxes. It's from the Winkle Formation. It seems to have been a contemporary of Mapusaurus. It's a more basal Giganotosaurini, but it's still closer to Giganotosaurus than Carcharodontosaurus is. Meraxes sounds like it's Latin, but it's actually just the name of a dragon in some nerd books for nerds. But it preserves the back of the skull. It has a squamosal, it has a quadratojugal. The skull is pretty complete except for the premaxilla. It lets us say, no, this is what Giganotosaurini skulls looked like. They look pretty similar to Acrocanthosaurus, actually. Now, I should be clear, the lateral temporal fenestra of Meraxes is very large. The bar underneath it is very long. It's just not as absurdly enormous as was getting reconstructed for Giganotosaurus or Tyrannotitan before this. One effect of the ever-lengthening reconstructions of Giganotosaurus' skull was that it stayed ahead, no pun intended, of Tyrannosaurus, which is interesting because in the original 1995 description, they listed a length of the femur that was like 6 centimeters longer than Tyrannosaurus, but that's been revised, and it turns out that Giganotosaurus' femur is like exactly the same length as Tyrannosaurus's. Both are 137 centimeters long. This toy's thigh and shin proportions look pretty good, actually. We have a complete femur and tibia from Giganotosaurus. We have a complete hip, but again, we don't have good figures or a detailed description of it. It appears to be very similar to the hip of Mapusaurus, which does have good figures. Broadly similar to the hip of Meraxes as well. The main difference is that Giganotosaurus's pubic shafts are not laterally compressed like those other two animals. They're more round. I don't know what that implies. But there's a quirk of the femur in Giganotosaurus and Mapusaurus that doesn't show up in Tyrannotitan or Meraxes, the more basal animals, which is that the fourth trochanter on the back of the femur is very small. the shape of it, having it be sort of a low ridge as opposed to a more fully developed wing, is similar to other large carnosaurs, but having it be so small and weak. Everyone who describes these femurs points out how small and weak the fourth trochanter is, but nobody goes to the next step and says what the functional implication of that is. We've talked about this process before. It anchors large muscles, possibly the largest muscles in the animal's body, for pulling the leg back during walking or running. The caudofemoralis longus attaches to sort of the inside of the femur and to the bottom and sides of the tail. The caudofemoralis brevis attaches to the outside of the femur and runs up to the base of the tail and parts of the hip. Now, conventionally, when you have a bone that is associated with a muscle attachment, the larger the bone, the stronger the forces that were acting on that muscle. So, having such a gigantic animal with a very underdeveloped, seemingly, process is really surprising to me. Giganotosaurus also has these grooves on the transverse processes of the anterior caudals, that is the anterior tail vertebrae. I don't know what that means. Maybe it's a muscle attachment for this muscle that wraps around the caudofemoralis longus. That runs pretty much from the ischium to the transverse processes of the tail, but it seems like the extensive research that we have on how giant coelurosaurs like tyrannosaurs move is only of limited use for Carcharodontosaurids because they seem to have had a different strategy in some ways. Now, what running means for an animal this size is somewhat relative. As a rule, with theropods, the longer the shin and foot bones are relative to the length of the femur, the more cursorial the animal is, the better adapted for running it is. We don't have foot or toe bones from Giganotosaurus, and its relatives send mixed messages. Meraxes is proportioned more or less like Acrocanthosaurus or large specimens of Allosaurus with relatively short feet. Tyrannotitan preserves part of a foot bone, but we don't really know how long the entire foot bone would be. And Tyrannotitan's shin is noticeably shorter proportionally than Giganotosaurus's, so I don't know how much guide it would be anyway. Mapusaurus preserves complete foot and toe bones, but they are proportionally very long compared to its body. Now, how could that be? Well, it's because Mapusaurus comes from a bone bed with multiple individuals represented at multiple sizes, and all of the foot and toe material comes from the smaller, younger animals. Theropods, when they're young, have proportionally rather large feet. They grow into them like a puppy dog. So, presumably, the very long, almost concavenator-looking feet that you see on this toy might be based on the Mapusaurus material, and that, as far as I can tell, is unreasonable. We would probably expect that Giganotosaurus would have proportionally short feet as an adult. So distinctly different from the very large feet that you see in the Odano mount, and very different from these long-footed toys. I should point out, objectively, these are still very large feet, just because it's such a huge animal. It's just proportional to its legs is the qualitative statements I'm making. We've mentioned before that workers constructed cursoriality scores to qualitatively assess whether a particular theropod was a good or a bad runner. Acrocanthosaurus was included in that data, and it's fairly poor. It's not a slouch like some animals, but it's definitely a worse runner than like a Tyrannosaur. Giganotosaurus seemingly would have had even shorter lower leg compared to its femur, so probably even worse of a runner. And while we're talking about the feet and toes, you sometimes see reconstructions. I suppose this toy is doing it. It's kind of hard to tell because it's sunk into the substrate, into the ground. I guess this toy is doing it, but you'll see Giganotosaurus restored with kind of dainty toes with very flat claws on the ends of it. I'm not sure, but I think that's based on Spinosaurus B material, because there was a brief period where that foot material was attributed to Carcharodontosaurus, and that might have carried over into reconstructions of Giganotosaurus. I don't know if that's happening, but thought I would mention it. Actual Carcharodontosaurid claws are robust, curved things, though there is actually some variation. Meraxes preserves this very large second toe claw. It's not similar to what we see in like dromaeosaurs, because in dromaeosaurs the toe bone that the ungule sits on is also modified to allow them to raise the claw up off the ground, but the claw is shaped differently in cross-section. It's got like a sharper bottom margin on it than the other toe claws do. Now this is in contrast to Tyranotitan, which preserves a toe claw which has consistently been referred to as the second toe claw, the second ungule, but it's really, really small. And every other toe bone of Tyranotitan has moved around a little bit between the 2005 description and the 2015 more detailed osteology. So it's possible, I guess, that they might have misidentified that claw. Maybe it's an unusually large dew claw even. But it seems like the ungules, the claws of Giganotosaurini were pretty variable. Now, atop those ungules were the keratin nails. This can be somewhat confusing because ungule literally means claw, but it actually is supporting the end of the toe, the fleshy part, at its base, and then the keratin sheath extends quite a bit further than the bone itself. We have some soft tissue preservation from a more basal carcharodontosaurid from Spain called Concavenator, which has the ungule and the claw actually mostly embedded in the flesh of the toe pad. Like, usually when you reconstruct a theropod toe, it looks like this toy, or like an emu or an ostrich, where the claw is extending quite a bit further from the flesh. But Concavenator seems to show a toe pad that extends pretty far along the sides of the claw. It's really only the very tip of the nail that's fully outside of the flesh of the toe. So if that's any indication of what Giganotosaurus had going on, its toes would have had pretty substantial beams. Another place this toy could stand to have more flesh is the base of the tail. The Safari 2017 toy actually does a bit better than any of these other ones, but even if the fourth trochanter indicates decreased reliance on the cauda femoralis longus, the base of the tail should be much more muscular than this. The tail at its base should be nearly as wide as it is tall, and that thickness continues pretty much to the middle of the tail, where the transverse processes leave off. As I mentioned, we don't have a complete tail from Giganotosaurus. We have a good chunk of it, but it hasn't been described or figured in detail. We can fill in some of the tail from Meraxes, but Meraxes' tail is kind of weird in some respects, which we'll get to. We may want to fall back on like Acrocanthosaurus for reconstructing the missing chunks of Giganotosaurus' tail. Like other giant theropods, Giganotosaurus' spine was extensively pneumaticized. It had an air sac system running across it. Tyranotitan shows that there's actually a separate abdominal set of air sacs, and then another set once you get to the hip. And Giganotosaurus shows not true pluricells, but pneumatic depressions on the anterior caudal vertebrae at the base of the tail. So this is another time that giant theropods had their air sac system extending into the tail. Now, when I say air sac system, that might imply an avian-style flow-through lung, which might imply a high metabolism and a high activity level. Do we have any research on that? A little. In 1999, some researchers sampled a bunch of bones of Giganotosaurus looking for isotopes of oxygen. They figured that they could measure the ratios of these two isotopes of oxygen and determine what temperature were the bones in life, how much did they vary from the core temperature of the animal, and how much did the temperature of the bone vary over time. They found that it is consistent with a bird's metabolism. If you were to scale that up to the size of a Giganotosaurus, it's sort of in between where we would expect a mammal this size and a reptile this size to be. Problem is, that's been challenged on methodological grounds. It turns out that those isotopes actually can be completely messed up by fossilization. Someone should probably go back and actually sample the teeth to do this study, because it turns out the enamel of teeth actually protects the isotopes better than other bones. There was a study of the bone tissue, the histology, of a bunch of giant theropods in 2020. They were trying to determine whether all giant theropods reached those gigantic sizes in the same way, and they do not. That study even included as yet unnamed Meraxes material. Now, they showed that unlike the giant coelurosaurs, the tyrannosaurs, carcharodontosaurids do not have an initial growth spurt and then a plateau. They just have slow, steady growth throughout their life that also slowly tapers off once they hit the end of their life. It's similar to what we see in ancestral dinosaurs, except in this case, it's producing giants. This research also indicates that Meraxes was older than me? Like, the way that they measured its growth rate was to look at the lines of arrested growth in the bone, where it's seasonally getting deposited more or less based on how much nutrition it's getting. And the innermost lines of arrested growth in the bone had been obliterated, so they don't actually know, like, exactly its age, but the Meraxes specimen must have been in its late 40s or maybe as old as 53. So even if we assume that our much larger Giganotosaurus is growing faster in absolute terms than Meraxes, it was probably even older than that. It could have been pushing 60. This squares somewhat with earlier research on growth in Mapusaurus. As I said, we have multiple individuals of multiple ages. Workers wanted to know whether the entire skeleton is growing at the same pace, and it is not. While most of the animal is paramorphic compared to its ancestors, it's growing faster, it starts growing earlier, and it keeps growing longer into its old age. The arms specifically were paedomorphic. They start growing later in the animal's life, grow more slowly, and leave off growing earlier. So in this one respect, and nothing else, this toy, which when we were first sent this, I thought it was a Megalosaurus, but it's actually a knockoff of what is supposed to be a juvenile Giganotosaurus. It's actually kind of right about the size of the arms, where they've reached adult size, even though the rest of the animal is gonna keep growing. As you probably noticed, this produces very tiny arms. This toy's arms are about right, I think. So we don't have any arm material from Giganotosaurus, but we can infer the size of the arms from the size of the shoulder elements, which we do have, and from related animals from Tyrannotitan and Mapusaurus and finally Meraxes. I will say that the hands on this toy are entirely too large, especially the claws. In fairness, we didn't have a good idea of the scale of the fingers relative to the arm until Meraxes, but based on like Acrocanthosaurus or even Allosaurus, we would have known that it wasn't just 3 equally long fingers with 3 gigantic claws. And maybe that's a level of detail thing because they can't have little sharp meat hooks on a toy. But Meraxes confirms that like in Allosaurus or other 3-fingered theropods, the first finger was the shortest but had the largest claw, and the third finger had the smallest claw. Astonishingly, all of these toys have the hands facing one another. I don't think we've ever had that happen, where none of them have the hands pronated down, which these animals could not do. Oh, I guess this one kind of does. Okay, I take it back. But this toy's chest and shoulder area is entirely too small. And if you look at the Odano reconstruction, which I'm going to continue calling that, even though like I recognize that multiple people worked on that, and everyone who mounts a replica of that is going to have to make like judgment calls about how do you pose it, how do you articulate some of the bones, but those all have this very small coracoid and a relatively small scapula. And it turns out, as of the more detailed description of Tyrannotitan, Giganotosaurus's scapulocoracoid was broken. It was actually much, much bigger than we thought. The original description suggested that the scapula was not fused to the coracoid. It's actually that it was broken right where we would expect the margin between those bones to be. So we didn't even notice that, no, the entire like front and bottom portion of the coracoid is missing from this animal. And it makes sense for Giganotosaurus's shoulder bones to be pretty robust because the arm bones we have from Meraxes and Mapusaurus are robust with prominent muscle ridges. So even though they were small, these arms had a lot of meat going on. Also, this toy's arms seem to be too far forward, even with the old dinky coracoid. Like, there's not enough room here in front of the arm for the chest muscles, I should think. Assuming the reconstruction on the mounted specimens is true in this regard, the torso of Giganotosaurus would be pretty deep. Like, the ribs are, compared to like a Tyrannosaurus, pretty flat-sided. So you wind up with this pretty boxy looking torso, and I don't think this toy has the torso deep enough. We have gastralia from Giganotosaurus, which are those belly ribs, but none of the mounts actually include them, which is not uncommon. Gastralia are very difficult to mount because they're these spindly little bones, and there's a bunch of them, and they don't articulate with any other bones. We don't have figures of these bones, we don't have detailed descriptions of these bones, other than that they co-ossify forming V-shaped chevrons, but that happens in a bunch of theropods. As usual, the exact position of the shoulder is open to some interpretation because there's no bony contact between any of the shoulder bones and the rest of the body. The shoulder blades just kind of wrap around the ribs, but conventionally, people will mount the shoulders really, really close to the bottom of the throat, and it doesn't seem like it leaves enough room for the throat. Whereas more modern reconstructions will have a pretty deep chest. On that subject, this toy lengthened the neck at the expense of the torso? Put another way, there's some dorsal vertebrae acting as cervical vertebrae, which is ironic because the last few cervical vertebrae were dorsal-like. In Mapusaurus and Giganotosaurus, the last few neck vertebrae are very short, front to back, and have sort of a makeshift secondary articulation, which is a load-bearing adaptation. The neck vertebrae are also episthocelic. That means that they're a ball and socket, where no matter where in its rotation it is, a vertebrae's center of rotation will always be inside the vertebrae behind it. It's a load-bearing adaptation. It means that it doesn't have to trade flexibility for strength, at least in this respect. The rest of the spine did make that trade-off. In Carcharodontosaurids, we have very high neural spines. Exactly how high varies, but in Giganotosaurus, they are robust and rectangular in cross-section, which, if mounted skeletons are to be believed, they're actually even wider than in Mapusaurus. They're like these giant cubes extruded on the tops of the vertebrae. They have prominent muscle scars, and all along the spine we would see interspinous and supraspinous ligaments forming kind of like a suspension bridge, holding up the animal's mass using the neural spines as struts. This is broadly similar to what we saw in like dicrasaurid sauropods, except there it's supporting just the neck, whereas here it's supporting the entire front half of the animal and the entire back half of the animal, and both systems link together and are anchored at the sacrum over the hip. The anterior portion of Meraxes' tail has neural spines with partial co-ossification between the first and second and third and fourth vertebrae, and the anterior caudals have secondary articulations. So unlike Meraxes, which has a completely co-ossified sacrum, Giganotosaurus's sacral vertebrae are separate except for some of the neural spines. So if it was having strain pulling at the sacrum, holding up the tail and holding up the front of the body, that makes sense. That's where the strain would be, is at the neural spines. How much weight was this system holding up? Well, that's open to some interpretation. Back in 1995, Correa and Salgado estimated its mass at 6 to 8 tons. You may notice that that confidence interval is the size of a small truck. Subsequent estimates have been similarly all over the place. There have been estimates as low as 4 tons and as high as 14. Currently, a reasonable estimate appears to be somewhere between 7 and 9 tons. There are fundamentally two methods of estimating the mass of an extinct creature. You can measure a bone on your fossils and a bone on a living animal, and since you can weigh the living animal, you can then make an equation to then calculate the weight of your extinct animal. The problem is, there are no living animals that are proportioned like a Giganotosaurus, so you're going to have a very wide confidence interval trying to estimate its mass that way. The other method is volumetric. You start with a very rigorous reconstruction of the animal and figure out, the muscles would have this density, the lungs and air sac system would have this density. You can even, with modern computer modeling, have like minimum and maximum envelopes that the flesh would have and get a volumetric mass estimation that way. This is a much more rigorous method, but it's only as good as your skeleton. And to do this method with Giganotosaurus, we would need a detailed osteology of the animal, especially since we would also want to then check, using finite element analysis or something like that, can the bones actually take the strain of hauling around a 9 or 10 ton animal? Or you could just plonk a toy into a 3D scanner and calculate its volume that way. Which is what some workers in 2021 did. And ordinarily I wouldn't mention this paper because charitably it is a proof of concept. Uncharitably it's a waste of time. But the toy they used to calculate the mass of Giganotosaurus was this toy. The 2007 Carnegie Safari Limited Giganotosaurus. Now, you could do worse than this toy as far as representing Giganotosaurus' anatomy. Exhibit A. Exhibit B. But compared to volumetric reconstructions of Acrocanthosaurus from a decade ago, it should have been obvious that this toy is emaciated. There's not enough meat in the torso area. There's not enough muscle on the hips and the tail. There's definitely too shallow of a torso. These are not minor problems. These are the things the paper was measuring. The authors claimed that this toy was based on recent and accurate reconstructions, and maybe that was true in 2007 when it was made, but this paper is from 2021. Even before Meraxes, it should have been obvious that this toy has some problems. I had all that to say about the neural spines, but again, we have no good figures and only scattered descriptions. The height of the neural spines is inconsistent across different reconstructions. Some people have them approximately like this, it's kind of middle of the road. Some people have them really long, like almost Acrocanthosaurus in length. I think that's based on Tyrannotitan, which does have one complete neural spine still attached to the sacrum, but we would need a complete osteology of Giganotosaurus to tell if that's the scale that we're looking at for this animal. In the classic 90s reconstruction of the skeleton, the neural spines on the neck are actually pretty short, and that's inconsistent with what we see in Acrocanthosaurus, obviously, but Meraxes and Mapusaurus as well. The Mapusaurus description mentions tall, wide neural spines on Giganotosaurus's neck vertebrae, at least in the middle of the neck, which sort of squares with what we see in Meraxes or Acrocanthosaurus, and Mapusaurus for that matter, where the neck vertebrae at the base of the neck are sort of squished to allow it room to curve upwards, which is how the animal would have habitually held its neck. It appears that, like other giant theropods, Giganotosaurus had long epipophyses on the front neck vertebrae. These are like levers that are used for elevating and for twisting the head around. And regardless of how long we reconstruct the neural spines themselves, the neck of Giganotosaurus was clearly very muscular. If we carry that idea tailwards, between the ligament system and the muscles running between the transverse processes and the neural spines, I'm not even sure you would see much of a dorsal crest along the top of the animal. It might be more like what we see in this toy, where it's barely visible, unless it was supporting a hump. You see, in Meraxes, the sacrum has this sigmoid. It's got an M-shaped sort of a dip in it, and Acrocanthosaurus shows a less pronounced version of that as well. If you look at Conchovenator, that has like an extreme version of this, where there's a whole sail in front of the hip and then another one behind it with a gap in the middle. So authors have suggested that the ligament system in Conchovenator was like tensioned at that sacral gap, where adipose tissue was weighing down on it there, which would imply that when you reconstruct Conchovenator, that whole space should be filled in with fatty tissue. Those authors stressed, no pun intended, the need for finite element analysis to test whether that's actually the stresses that were happening for Conchovenator's spine, but if Conchovenator having a somewhat overbuilt spine for an animal that size is evidence of a hump on its back, then wouldn't Meraxes having a somewhat overbuilt hip and anterior portion of the tail? Remember, it's got those secondary articulations and those neural spines that are partially co-ossified. Is it so adapted for load bearing because it's bearing a hump? Also, the medial portion of Meraxes' tail in the middle, like starting at the 11th vertebra and going onward, the neural spines are noticeably shorter than you'd think they would be based on how long the ones in the proximal caudals are. So if the tail is kind of shrimpy starting at the middle portion, why is the proximal portion of the tail so overbuilt? Maybe I've been staring at this material too long and have descended into madness, but what if Meraxes had like a hump in the middle of its tail? Wouldn't that be something? We don't have any weird structures like that for Giganotosaurus. At least, if we did, you would think the authors would have mentioned them. But if storing energy in adipose tissue, storing energy in fat, was a strategy that some Carcharodontosaurids had, it might be reasonable to infer that Giganotosaurus would benefit from that, because Candeleros was only seasonally productive, and Giganotosaurus might have had trouble getting through the dry season. Candeleros is a varied formation geologically. There's stacks of different rock deposited in different conditions. Generally, this area of South America in the middle of the Cretaceous was warm and relatively dry, averaging around 15 degrees Celsius year-round, and having a short wet season in February. But that wet season seemingly dumped a lot of water. Workers estimated annual rainfall above 76 centimeters, which in the Cenomanian, global sea levels were the highest they've been in the entire Phanerozoic, so that would make sense. But since most of that water was coming down from the mountains during the short wet season, we have very strong floods that could knock over whole trees, and we have preserved tree trunks in Candeleros. This whole basin was a terminal fan system, or actually several overlapping terminal fan systems, where water flowing down from the forming Andes Mountains would spread out and slow down, kind of like a river delta, except it's meeting dry land instead of the ocean. And it would evaporate, leaving behind its sediments, leaving behind sand or silt. That sediment got picked up by the wind and deposited into these large areas of dunes. So we have this interesting situation where we have these channels of vegetation separated by pockets of dunes, pockets of ergs, which is what you call that. And I say pockets, but the largest one was like 30 kilometers across. It's called the Cocorcum Paleo Desert. Now, neither Giganotosaurus's bones nor its footprints are found out in the dunes, but we do have isolated teeth that might suggest it ventured out that way sometimes. Giganotosaurus was out in the floodplain. Again, floodplains are good for preservation. So dunes and these floodplains actually shade into one another because obviously, one is feeding the former by producing the silt that gets blown away, but over millions of years, as the humidity varies, the same spot in Candeleros will go from dry dunes to wet dunes, which are also good for preservation because sand will collapse into the channels between them, to alluvial or fluvial plains, to even swampy conditions with seasonal lagoons. Candeleros was a thick formation with varying environments represented, but as far as I can tell, Giganotosaurus was from a semi-arid to subhumid savanna type of environment, not too dissimilar to the Gran Chaco Plain today, except obviously without grass, which would seasonally flood and bloom with flowering plants, probably forming the understory, and then cypresses and Araucarian conifers up above. Now, since its environment was relatively warm and relatively dry, we can probably infer that such a gigantic animal would have no need for insulation, so reconstructing them without extensive feathery covering is probably the safest bet. We do have skin impressions from Concavenator, which I think is the closest relative that preserves any. It has rectangular scales on the bottom of the tail, but it also preserves a podotheca, which is those shield-like scales on the feet of birds. And if the ones that we see in Concavenator are homologous with the ones in birds, those develop from feather play coats. So maybe it's secondarily featherless? It's also possible that even if it was mostly featherless as an adult, it might have had more extensive covering as a chick when it was small and more vulnerable to like those colder dry season nights. There's research in 2021 looking at, well, a lot of theropods from Italy, but part of it looked at the problems that arise when you include immature animals in a phylogenetic analysis alongside mature animals, and they found that some specimens that have previously been recovered as Coelurosaurs, as compsognathids in particular, might actually be more basal animals. This squares with an initial idea about an animal called Sciuromimus? I've only seen it written. I think it's Sciuromimus. Where it's got this really fluffy body on it, but it seems to actually be a juvenile megalosaur of some kind. I bring this up because there's this days-old hatchling from the Albion of Italy called Scipionix that might actually be a Carcharodontosaurid. It has a few traits that we would associate with basal Carcharodontosaurids, like Eocarcharia or something like that. And If that's true, and some of these little nippy dinosaurs are actually juvenile Carcharodontosaurs, then technically we've been restoring Carcharodontosaurids with feathers for a while now, because it's almost conventional to restore compsognaathids that way. I'm obliged to mention that Concavenator also preserves these knobs on the ulna, on its arm bone, and no matter what those represent, they are odd. If they are quill knobs, it's weird that they're on that side of the bone. They're in the position that they are in like modern moorhens. They're not on the back of the ulna like you would expect in other theropods. If they're muscle scars, which some authors think they are, it's weird that they're forming scars because the muscles that attach there usually don't do that. We would want histology, tissue analysis of the bone, to really clear this up, but they would either have to cut into the ulna, which they are apparently unwilling to do because that's destructive, or use non-destructive scanning methods, but as far as I can tell, the slab that it's embedded in can't fit in the machines. So it's possible that you could restore Giganotosaurus with some kind of quills or even actual feathers on its arms, but somebody's gonna have a problem with it. Since we're talking about integument, let's talk about the cranial ornamentation, this varies across all Giganotosaurini, but there are some commonalities. We can look at the shape and texture of the bones we have to look for what are called osteological correlates, which is where the different structures that are in the skin leave marks on the bones. I don't actually have to do that because Mark Whitten already did that on his blog for Giganotosaurus specifically. I was somewhat vindicated because he stressed a bunch of the same stuff I've been harping about, how the material is incomplete and a lot of it doesn't have proper figures, and people could reasonably come to very different conclusions based on what we have. But it seems that most of the top of Giganotosaurus' head had some cranial ornament or other. The lacrimal has a long ridge-like horn on its dorsal surface. We have the usual caveat here about like the extent of a keratin sheath can surprise us based on the bony core. It might be very close or it might be very long. This toy has ornamentation going down the lacrimal and postorbital. We don't have any correlates for that. The bones are smooth there. These could just be like feature scales and therefore they wouldn't leave marks on the bone underneath them. You sometimes see a claim in like popular sources that Carcharodontosaurids or allosaurids more generally don't have binocular vision, and no, they did. Like, look at an Acrocanthosaurus skull from above. It's got sort of a Y shape to it. They didn't have the binocular field of view that you see in like a Tyrannosaur or a Troodontid, but they still had some. Speaking of the senses, workers made an endocast of the cranium of Giganotosaurus to study its brain. Like most non-avian dinosaurs, the brain didn't actually fill that cavity, but we can say some things about the general proportions of it. The only comparative study of the cerebral anatomy I could find was comparing the size of the olfactory bulb at the front of the brain to other animals, and surprisingly, they found that Carcharodontosaurids have a relatively average sense of smell for theropods. That's surprising to me because, like, look at their sinuses. The entire front of their face is just sinuses. I would have expected them to have comparable sense of smell to like a Tyrannosaur, but apparently not. On the subject of sinuses, unlike Carcharodontosaurus, who lengthened the narial fossa going back from the external nares, Giganotosaurus and its closest relatives extended the next chamber back in the antorbital fossa, and it actually extended up into the nasal. It had these pneumatophores and recesses sort of pneumaticizing the nasal. The unfigured nasal bones are the oddest part of Giganotosaurus's regalia. I really wish that we had good images of these, but based on the mounted specimen and on Mapusaurus, the classic, like going back as far as the Gurney illustration, way of restoring the nasals of Giganotosaurus with like a row of individual spines is definitely not the case. Sometimes you see, like in this toy, where it's actually paired horns. Sometimes they're like this, where they're just sort of little nubs. Sometimes they're full-on spikes. In the Odano restoration, the rugosity, the wrinkliness on the sides of the nasals leaves off, and the center of the bone where they meet in the middle is smooth. Apparently that's not actually the case. Based on Mapusaurus, we can see that the rugosity on the nasals wraps the entire bone. It sort of winds up looking like a radiator. It's got like these fins going all the way across it. Witten argues that when bone is getting laid down this way, that's because there's a cornified pad or boss growing at a shallow angle to the bone, similar to what we see in modern Cape buffalo or musk ox, where it's not really a horn, it's just kind of a big pad. There's a somewhat similar situation going on behind the lacrimal horn, where we have the palpebral bone roofing the eye socket, which is tilted back and has a wrinkly upper surface, and then there's a postorbital brow-looking area, like in other Carcharodontosaurids. The texture of that part of the skull is undescribed for Giganotosaurus, but visually it looks like what's going on in other animals, and if that was supporting another boss, even if it was like shading into being scale-like, it would give the whole animal kind of a worried expression. I think Witten calls it world-weary, which this toy, I think, communicates pretty well. This animal has the right facial expression for a Giganotosaurus. Again, we don't have a squamosal from Giganotosaurus, so I can't say how this toy portrays like sideburns of ornamental structures going down in front of the ear is reasonable. Like, I guess it's possible. What about the unadorned parts of the face? Well, the snout tip got my attention. It hasn't been described because, you know, the premaxilla has never been properly figured, but from the mounted specimen, it seems to have a similar texture to the very front of the dentaries, where the chin is. This has sort of clusters of foramina together with a wavy or hummocky texture of the bone, and in other theropods, that kind of texture has been correlated with large scales with sensory organs in them. Is that what's going on with Giganotosaurus? I do not know, but if it was, that would make sense for an animal that's having to tear meat out of carcasses, or maybe just for, like, social signaling, or maybe for testing the temperature of its nests if it buried its eggs. Moving backward, Witten pointed out that other Carcharodontosaurids show a pretty rugose texture on the maxilla, which Giganotosaurus's is relatively smoother, but that might just be due to size or individual variation. But it seems like Carcharodontosaurids would have had a more flexible area of scaly skin over the sinuses, you know, underneath the nasal ornamentation, but above the bar-like jaw area, and then another flexible area beneath that where you get down to the tooth row where there would have been fleshy lips. The part of Giganotosaurus's maxilla that would have a row of foramina to feed nutrients to lips is largely broken off, but looking at the dentary, it does have a row of foramina set in a furrow. So again, we're looking at an animal where, with the mouth closed, you would not see the teeth poking out. There's something of a trope. I think this comes from that specimen of Acrocanthosaurus that has a complete skull, of showing Carcharodontosaurids with like saber teeth, like with the upper teeth extending down below the bottom of the chin. But that's because that Acrocanthosaurus was dead. Like, it is unlikely that these animals habitually held their mouths such that their lower teeth were digging into the roof of their mouth. That would hurt. It is tempting to call the Cenomanian of Gondwana a throwback or a relic. It's in some ways kind of the last gasp of the Jurassic, because you've got giant allosaurids and like giant sauropods, just like we had in, you know, Morrison Formation in the United States or so forth. But that label incorrectly implies that like things were winding down, when actually these animals were the largest they had ever been. But over the course of what seems to have been a very long life, Giganotosaurus would have been carving out a niche among different animals as it increased in size. As a juvenile, Giganotosaurus would have seen competition or maybe even predation from two little Maniraptorans, Alnachetri, which is an alvarosaurid similar to Alvarsaurus, and Buitroraptor, which is a long-snouted unenloging dromaeosaurid. Candelaros has a lot of small carnivorous notosuchians like Auroripasuchus, which are short-faced terrestrial kind of fox-like crocodile relatives. There's no small noasaurid, which is weird because we would expect, based on the Winkle formation, to see a counterpart to Winklesaurus in Candelaros, but we do have a approximately 3-meter long basal coelurosaur called Bicentenaria. We also have indeterminate pterosaur tracks that have been undescribed, so I have no idea what size of animal we're talking about there. As far as prey, we have tuatara relatives, limbed snakes, turtles, frogs, and lungfish, presumably in the wet season, and non-therian mammals like Chronopio, which kind of looks like Scrat from Ice Age. It's got these little saber teeth. As a subadult, Giganotosaurus may have preyed on Jacopele, which is a little armored ornithischian of some kind, and an indeterminate little ornithopod, probably similar to Anabacetia from the Cerro de Sandro Formation. It would have been competing with Neosuchians. As far as I know, these are similar in form and ecology to modern crocodiles, but again, I couldn't find any information on their size. And we would expect competition from like a mid-sized Megaraptoran or a Neovenatorid, since Winkle Formation has Gualecho, Aeonaraptor, and some other third thing. Especially since Candeleros does have a small, indeterminate abelosaurid that's a counterpart to Winkle's Ilocalacia and Tralcosaurus. Maybe we just haven't found it yet. There's circumstantial evidence suggesting that Mapusaurus lived in mixed age groups, and if Giganotosaurus was doing something like that, it might be able to broaden the kinds of prey it could take and protect itself from animals like Ecrixanotosaurus. This was a large, 7 meters or more abelosaurid. The name means explosion-born reptile because they dynamited the holotype, but it's built like a bruiser. It's the size of Carnotaurus, but with a proportionately larger head, and it puts the lie to the idea that abelosaurids only got gigantic once the Carcharodontosaurids were gone. But apparently there was sufficient prey for 2 large theropod genera. There were abundant Rabachisaurids, including the quite small Nopscospondylus, whose holotype specimen is lost to us, and the more respectably sized Rheososaurus and Limesaurus, the latter of which also occurs in Winkle. There was also an approximately iguanodon-sized ornithopod known only from its tracks. The largest prey were the large and giant sauropods. You sometimes see Andysaurus described as a mid-sized sauropod, but it's huge. It's just in the unfortunate position of being compared to the Argentinosaurus-sized Sapala-Titanosaur. Andysaurus was a relatively gracile animal with a long tail and broad teeth, whereas the Sapala-Titanosaur is approaching the size of the largest Longosaurus, even though it's currently recovered as a rather more basal animal. I keep calling it Argentinosaurus. It's actually not clear if it is. This material was described in 2021, and some of it is still in the ground, and very little of what we have actually overlaps with the known material from Argentinosaurus, so it might actually be a second specimen of that genus. As I said, this was one of the largest land animals known, so it's difficult to imagine even a predator as large as Giganotosaurus posing a threat to such a huge mountain of an animal. But I suppose they weren't immortal. You may reasonably ask, if these giant titanosaurs and giant allosaurids were riding so high, if Carcharodontosaurids were at their largest and most diverse right before they disappeared, well then why did they disappear? There's been a lot written about that, but nothing particularly conclusive. People have tried to correlate it with the decline of sauropods, but that just moves the problem, because then you're like, well, why did the sauropods decline? And there seems to have been a turnover in flora, where angiosperms take over from the old guard of plants, but it's not clear why that would correlate with a decline in sauropods when they had survived floral overturns before. What I can say is that we might be taking too broad of a view of this. You know, we're looking at this in hindsight, but these were separate faunal turnovers happening in different places at different times, and we need not assume that they all had the same global cause, or at least not were entirely global in cause, just because they all resulted in allosauroids dying out. That might seem ambiguous, but that's the closest I can come to an answer, and if that isn't the theme of this episode, I don't know what is. I probably seem frustrated, and I guess I am a little bit, because I didn't intend to spend quite this long writing the episode, but I can't be too mad. Like, it's not like these authors have been idle. They've spent the intervening decades publishing on every other aspect of this environment. We have a much, much more complete picture of the New Ken Basin, of Carcharodontosaurids as a group, than we did when Giganotosaurus was first described. And it would be pretty hypocritical of me to criticize somebody for taking a long time to write something about Giganotosaurus. When this animal was first described, we had precious little information about its environmental, morphological, or even temporal context. Whereas now, The stage is kind of set for Giganotosaurus to step into it whenever a full description of this animal comes along. And I want to thank you guys for watching Your Dinosaurs Are Wrong. Please remember to like, comment, and subscribe, and I will see you guys next time. We would like to extend a special thank you to these individuals who have gone above and beyond to support this show. We could not have done it without you. Thank you.